Hello, everyone. This is Super Quantum Team, and we are happy to present you our project, Qubitcoin. I'm in Boston, and it's getting colder and colder. So this is one of the ways how you can stay warm and heat up your houses and apartments with GPU by running this new type of coins, which is called Qubit coins. Who are we? We are Super Quantum Team. This is Daniel Shatohin and David Nizovsky. They are students from Vanderbilt University, and myself, Mikhail Shalaginov, research scientist at MIT. And of course, we would like to acknowledge help and guidance from our friends, POWEX team, specifically Mikhail Dubrovsky, Anton Kovalov, and Bogdan Pinkovsky. And this is an open source project, so we invite everyone to join our team and to contribute and to develop further our projects. And this is the website, superquantum.io. Please go there and check more information about the Superquantum team, as well as the project we do together. In short, what we would like to do, if it's too long, don't read, we would like to develop GPU quantum simulators, bring them to the next level in the race of quantum computers. Quantum computers are trying to reach the quantum supremacy and create the performance gap between classical computers and quantum computers. And we think that quantum simulators were actually left quite behind. And by efforts of the Qubitcoin project, I think we can push further the performance of the GPU quantum simulators, both on the side of the hardware as well as on the algorithm, which could be performed by computing their specific quantum circuits. So that's a meme demonstrating that we are keeping up with quantum computers, and this in result would also push the quantum computers to develop further. As an agenda, we have here 4 parts. First one is about vision and idea. What is a qubit coin? Where it comes from? Then the second part, Daniel will go through the technical implementation. Then we'll show you a demo of what is the package we have currently developed and how does it work. So we'll deploy a node and a miner, and at the end, David will go through next steps, to-dos, communities, what are the upcoming events. And that's the question for the audience. What do you actually see here? And this thing, it dates back to the end of the 19th century, beginning of the 20th century. This is the Crookes tube. And at that time, that was a very interesting scientific object or toy, if you wish, and a lot of stuff came out of it, surprisingly. So if we go through the outcomes of the Crookes tube, you will see that for example, Röntgen, he accidentally in his lab, while using this Crookes tube, while studying what they can do, he actually noticed the reflection in the corner of his room, and then he noticed there was like the fluorescence coming from one of the plates, and then he was quite puzzled of what is happening, and he put his hand on the way of the beams coming from this tube. And then later the discovery went to the X-rays and all the upcoming technologies what we have right now. And you can see that also led to a fundamental discovery of the electron and atomic theory development, vacuum tubes. These are the early electronics, amplifiers, radio technology, fluorescence devices, CRTs, those displays, as well as mass spectrometry. So we think that actually quantum computer is the Crookes tube of the 21st century, in a sense that this is indeed a really cool thing to have, although on the other side, we don't really know what could it be useful for. Of course, there's like so many proposals of what we can accomplish with it, but still they're all under question. And that's why we think this is the great comparison with the 19th century device. So back in 2022, myself and Michael Dubrovsky, we participated in MIT Quantum Hackathon, where we had to work with quantum technologies. So then we're like, all right, let's have a look and what can we do with quantum computing? Can we apply it really as this Crookes tube to connect it with any other technologies? And among the most famous technologies or most hype technologies, we decided to stop on blockchain. Also, Michael had expertise on that side. He actually was involved in developing optical Bitcoin or optical proof of work. So first of all, I know some of you are familiar with Bitcoin and how it works, as well as the blockchain concept, but I would like to do a short review of what is it in order to proceed further with the concepts we're using here. So Bitcoin blockchain. Essentially, Bitcoin is the chains of blocks of different information. This information contains the transactions which happen between different parties, and in order to add a new block or to add this new piece of information, you need to solve a problem. And then there is a peers network which participates and competes with each other in solving a specific type of problem. And that after this problem is solved, then the block is added. And all the basics of the Bitcoin, they originally were described in the paper by Satoshi Nakamoto back in 2008. And what we have right now in 2024, so it's like almost 16 years after, we have a very secure system, which, for instance, is used for the currency and as an exchange, it's like the payment system. So if we look deeper into the Bitcoin and ask ourselves, what is the actually problem they are solving? And here is the answer. So that is known as the proof of work, or POW, also as the hash cache. And here is it shown like the full cycle. So you have the block of data with the information about the transactions. You also have the information about the previous block, previous hash, the block number, and then there is also nonce. So essentially, what these peers in the network, what they're doing, they're trying to find the nonce which would satisfy the difficulty. So this block of data is pushed through the hash function. Essentially, whatever you input into this SHA, as an output, you get a bit string of 256 zeros or ones. And interesting thing about this hash functions is that even if you change one bit in the original data, it can give you a completely different answer. So this task is difficult to reverse. Like you cannot really, by knowing what is the output, you can really get the input. And then you need to satisfy the difficulty condition. The difficulty condition is actually set in a way that the block is added if, for example, the output string contains a certain number of zeros. And that the difficulty is controlled by the total hash rate. So the more participants, the higher is the hash rate, in a way that one coin is released every 10 minutes, for example, for the Bitcoin. And that the Bitcoin is the first system which successfully implemented the hash cache. And the hash cache, it's the story behind it is that it was proposed even before that, back in 2002, in order to prevent the spam while writing the emails. So that, for example, when you want to send the email, you need to go through this loop of proof of work until you satisfy the condition, and then the email will be sent. So in a sense that you cannot really send a lot of emails instantaneously because you had to perform this proof of work or hash cache computations, which are quite costly. So then coming back to the quantum hackathon, we looked at how can we do cryptocurrency mining with the quantum computers. How can we bring them into the game? And So what we have done, we have essentially stretched out that's the original Bitcoin cycle. Instead of one hash, we had now two of the hashing functions, and then between them, there is a quantum algorithm. And what quantum task should we solve? That was the fundamental question for us, and we have tried several approaches from the hackathon where we basically just used a random quantum circuit. But recently, we came up with an idea that we can use a useful quantum task, which would also help the community in solving a specific set of problems. But before I go into the description, I would like also mention that this approach of actually stretching up the original proof of work, it's known as the heavy hash. And this approach is already implemented by one of the cryptocurrencies, Caspa. And Caspa is actually growing up, and it's already the trade amounts is about 12 billions in a day. And in that approach, they actually, instead of the quantum task, they have a matrix multiplication and additional task, which was originally proposed by the POEX team, by Michael Dubrovsky and et al. And it's really cool that it has been already implemented in the real cryptocurrencies. So what quantum task should we consider? What should we put in there? We would like to have it as a useful task, and we look through various directions of quantum computing, and we found that variational quantum algorithms look really attractive. First of all, they are quite versatile and then can be used in different applications. For me, specifically, the application of finding the energy states of the molecules, specifically finding the ground state, is really interesting from the fundamental point of view. And that's personally why I really attach to the variational quantum algorithms. Also, those algorithms, they actually involve both classical and quantum computers. So this is like a synergy between the two worlds. And if we go into a little bit of more details, what happens there in, let's say, an example of finding a ground state for the of the Hamiltonian, finding its eigenstates and finding the minimum one, what happens is, so we can write down the Hamiltonian for the molecule, and to directly solve this problem, it's a very tedious task. And what is usually done, you can try to find the wave functions and substitute into the Hamiltonian, then compute the integrals and get the final answer of this integral, which would be like the energy levels, and you do it until you find the minimum one. So all this optimization is essentially done by the computations are also done by the classical computer, and the role of the quantum computer is to probe or bootstrap the distribution of the states of the quantum states. And if you have a, let's say, quite large molecule or a lot of particles are involved, so this state is it's exponentially large. So that's why to probe this space, there is a use the parametric quantum circuit, which helps to converge and find this the states which would lead to the minimum energy much faster. So if we now look deeper into this parametrized quantum circuit, I feel like I'm explaining this Russian dolls approach, starting from the quantum task we're looking, then variational quantum algorithms, then what is the quantum circuit is used. So that would be one of the end parts of the smallest Russian dolls, which would sit inside. And traditionally, there is a hardware efficient ansatz, which is quite widely used as this quantum circuit, which performs the search or generates the candidates of the states which will be computed for finding the minimum energy. And what are the key advantages or key features of this particular ansatz on circuit? So this circuit has been primarily optimized for real quantum computers. So it's composed of single qubit gate, the rotational gates, this R, Y, and RZ, as well as the 2-qubit gates of C naught. So these are the native set of gates, and also the connectivities are quite straightforward. It's a 1D layers, and those quantum circuits are known to have like a minimum number of parameters which needs to be adjusted, and as a result, because of their size, they are quite noise resilient. So now this is the summary of our algorithm. So we are essentially stretching the proof of work by adding a quantum task inside, and the quantum task is about the computation of this hardware efficient ansatz, which is used in variational quantum encoders or quantum algorithms in general. So here what we do, the incoming hash, which is a 256-bit string, we break it into the pieces of 4 bits, and then each of these bits goes and defines what is the angular rotation for single qubit operations. And then we repeat those circuit a couple of times, and at the end, when we do the measurement, we essentially calculate the probabilities of each of the qubit bit in the state of 1. And that is recorded as a mantissa with in the specific like format, then it's converted into the binary code. And after that, we concatenate those outputs together and put them through the next hash. And as a result, when we do the difficulty check, it needs to satisfy that there is a specific number of zeros. And then if it's qualified, and then everyone in the network agrees that this was the right nonce, which generated at the end a certain number of zeros when it's went through this quantum algorithm, then the block is added. And now I will turn over to Daniil, who will talk about more technical implementation of that. And before I turn over to Daniil, who will speak about the technical implementation, I would like to say that we have a repo on GitHub, and this is it's based on the fork from the original Bitcoin. And please, you can go and use it. Here is the QR code how you can access it.
So in terms of the absolute difficulty, our quantum task, which we use for our quantum simulation, involves 16 qubits, which can easily be simulated on any modern GPU and even most CPUs. However, our achievable hash rate is still orders of magnitude lower than that of the Bitcoin due to using GPU and just involving more intensive compute tasks. And for the modern GPUs, it's in the ballpark of a few thousand hashes per second. However, our current difficulty level adjusts to it, and it still tries to issue 1 Qubitcoin block per every 10 minutes, just as the original Bitcoin network. And here you, by the way, can see the formula for the assert algorithm. Now you can ask, what do we actually use? What software do we use for conducting quantum simulations in our hash function? And the answer is the Qstate library, which is part of the NVIDIA Quantum SDK. However, if you want to achieve a higher hash rate and you know you can do it, or if you, for example, want to have a better hardware compatibility with your system, you can use your own simulation software instead. You can just integrate it into our existing mining software. To do it, this simulation library has to have a C API, and it requires you to re-implement 2 functions, which are directly responsible for quantum simulations for our hash. And when you do it, which is not that difficult if you're familiar with the software you're using, then you can just rebuild our binaries, specifically the miner binary, and then use it in place of the provided one. So yeah, that's it.
Okay, let's go to interesting part, to the demo. Super quantum. And here in the, yeah, it's like a lot of stuff. It was originally forked from Bitcoin. And if you scroll down to, there should be README. And at the beginning, there's like, in general, all the explanation of what is the project, what is the Q hash, how does it work. And if you scroll down, we have, I've just, for coming here, added how to start mining Qubitcoin. So here you would see the instructions on what do you do if you have Windows OS, or if you have already Ubuntu, you would need to install drivers for CUDA, install CUDA, then get those executables and run them. I think there will be a couple of missing packages which you need to install as well, but other than that, you can do it like almost within a half an hour or so. This is the miner screen. This is the node screen, and in order to deploy it, you would need to get the executables. They are on our website. So if you go to Super Quantum, and then scroll down, there is Qubitcoin. So to launch your miner and know the fastest way, you would need to download these files, which is Qubitcoin CLI, which is essentially like a wallet, Qubitcoin miner, and then the node. So we need to deploy the node, and then after that, the wallet and the miner. And the node needs to connect to one of the available ones. So the system works when at least two of the nodes are on. So that's what we have the two nodes working right now, and you can join to them. So every 5 minutes there's like a report on how many solutions have been submitted, how many of them like accepted. This particular node, it mined. I think I restarted it before. I mean, on average, they expect it to come like in 10 minutes, but since like at the very beginning, there's like some uncertainties of how fast the nodes can mine. And then essentially like this one already mined like one block. But I think there should be probably around like, let's see, when was the last block? Yeah, I think 43 was the last one, which was mined and almost right before we started. All right, maybe David,
Yes.
we'll talk about next steps, where we're going.
All right. So now let's talk about a crucial aspect of our roadmap, trading and market accessibility. We have a clear strategy for getting our tokens into the hands of those who will use them most efficiently. So we're taking a phased approach to exchange listings. Initially, we'll launch on decentralized exchanges, which will provide immediate liquidity and trading opportunities for the first users. After which, we'll be focusing on mid-level exchanges, and after this, obviously, top-level exchanges, hopefully. But here's what makes our token truly unique in the trading landscape. While you can trade it like any other cryptocurrency, basically, it's backed by something tangible, which is quantum computing power. Think of it like trading cloud computing credits, but for quantum computers. So this unique utility aspect makes our token particularly attractive to both traders and institutional users who need quantum computing access. This trading mechanism will work like this. Holders can either trade coins on exchanges or convert them directly into quantum computing credits. We're already in talks with several quantum hardware providers to make this seamless. And every coin will essentially represent a stake in the quantum computing future we're all here building. And as quantum computing becomes more and more mainstream, the demand for these commuting credits should naturally increase. So this creates an obvious, clear value proposition that exchanges and traders can understand easily. Remember, though, while trading is important, our primary focus remains on building real utility through quantum computing integration. We're trying to focus mainly on developing quantum simulations. So the stronger we make that foundation, the more valuable our token becomes in trading ecosystem. We are also thinking about going into direction of developing our own hardware, which will be focusing on better quantum simulations, and it will naturally represent ASIC of Qubitcoin, application-specific integrated circuit, which are currently used by almost every cryptocurrency that uses proof of work. Bitcoin, Kaspa, they all have their own ASICs for the most efficient mining process. But here's what really excites me, the potential for community-driven innovation. And we're here not just building a blockchain, we're trying to create a whole ecosystem where classical meets quantum, where software meets hardware, and where theory meets practice. And we want to hear your ideas, whether you are a quantum physicist or a blockchain developer, software engineer, or someone who sees the potential in this technology. There is a place for you in this community. We are always welcome. And our development roadmap is flexible because we believe the best ideas often come from unexpected places. I think that's it for our future plans. We will announce all the upcoming events in our channels of communication, which you can see on the next slide.
Yeah, here we have primarily a lot of discussions happen in like Telegram, Discord, and repo, which we can show you a little bit more details from there. There's like email, website, YouTube. I will put the tutorial. There is already a tutorial I can show you on GitHub, written in text, fresh, and just checked it and verified that everything works today. And we have also a blog to read more about this. So this is on Medium. There is actually a really cool story I have heard yesterday that at MIT back in 2014, I believe there were like two students who proposed to give some part of the Bitcoin. At that time, it was like a third of a Bitcoin to other undergraduate students to build a community. I think we are like really inspired by this generous step, and we also would like to share whatever we will mine today to share with you. So you would need to create your wallets and send it to us, so we would forward you Qubitcoins.